Hi everyone, in this recording we'll discuss hypothetical outcome plots. So hypothetical outcome plots are very useful when you want to communicate uncertainty for more complicated objects. So not just like one-dimensional means, but things like curves or networks or compositions. So to make things concrete, let's imagine you're trying to communicate uncertainty in a linear regression fit. So here I'm showing a supernova dataset. The y-axis, this is the brightness of the supernova that we see on Earth. These are a whole bunch of different predictor variables. It's not too important what they are. And what I'm drawing here, the black line is the linear regression fit, and this gray area, this is the confidence band. And so you imagine the line actually could have been shaped differently, but you think that the line probably lies within this shape, this band. Right? So this band is known by theory. But then for a lot of beginners, this is not the kind of shape that they would have expected, right? Kind of our intuition is if you want to communicate uncertainty in a linear regression line, wouldn't the uncertainty just be different parallel lines? Like, why isn't the band just exactly another straight line parallel to the original one? That's what most beginners think when you ask them, kind of show me the uncertainty in this linear regression fit. Right? A nice way to communicate the intuition around why it's shaped in this way is to show different hypothetical outcomes. So what I'm showing here is I've resampled the original dataset. So you just subsample. You take a bootstrap sample and then refit the linear regression on the bootstrap sample. Right, so you might double count a couple of the points. You might completely miss some of the other points. And in that way, you're simulating draws from the larger population, and you can get some uncertainty on the slope, right? And this begins to communicate why we have the shape that we had, right? So it looks almost the same, right? It's a little bit narrower here, and it's a little bit wider here. And kind of now the reason's obvious is that we have uncertainty both in our estimate of the intercept, so that's this variation, but also of the slope, right? And it's that variation in both of them together that leads to this curved confidence band. Right? The really nice thing is that this hypothetical outcome idea applies even in situations where there's no analytical formula to communicate the uncertainty. Right? All of this kind of linear regression type uncertainty, this is known in theory. You could have derived this without doing any simulation. But if you had a nonlinear fit, right, so here, this is another variable against magnitude. This looks like a pretty nonlinear relationship. So you want to use a nonlinear. Here I'm using a GAM to smooth the data. But there's no longer any kind of theoretical confidence band. So a natural thing to do is just to bootstrap. So here I'm using this sample outcomes function to draw 150 times bootstrap samples of the original data. So again, it maybe double counts a few of them, it maybe omits a few of them, and then it re-smooths using a different GAM. And then I save each of those outcomes as a draw, right? And I'm drawing each of those lines overlaid. Right? So now you get a sense, in another world, if you had gotten a new sample of supernova data, you wouldn't be too surprised just to see a curve that somewhere out in this region, you're not going to just imagine that this is this one fit that it has to lie through. Right. Okay, so this isn't actually a traditional hypothetical outcome plot. This is just kind of showing the bootstrap intervals. The thing is, when you look at it like this, you tend to just focus on the area. You don't really notice the individual outcomes, right? If you want to show the individual outcomes, a natural thing to do is to try animating, right? This is kind of a traditional hypothetical outcome plot. This is what is most studied in the literature. And what I'm showing is just separating out each of the runs and animating it. I'm using the ggAnimate package. These are the two main functions that allowed me to do the animation. So I'm just saying, go through frame by frame and show each draw. And it gives a sense of like, okay, out here it tends to be a little bit more stable, still pretty wiggly. out here it's way all over the place. So you get a sense that don't trust too much the direction of the smooth near the endpoints, right? So it focuses our attention on uncertainty in a different way than if you were just paying attention to the band. Okay. You can try to combine the two approaches, right? So here I'm showing the band, but I'm also illustrating each individual outcome and animating them on top. So all I did to do this is I created an extra layer where I keep the bands from all of them fixed, and then I have a second layer with a red line. Okay, now this wasn't discussed in the reading, but I think it makes sense considering everything else that we've done in the class. You could also imagine a dynamically linked version of this sort of hypothetical outcome plot. So what I've done here is I've run PCA on the raw values of these curves. Right, so each point here corresponds to one curve. When I brush over the points, it highlights those hypothetical outcomes. Right, so kind of look at the bottom half of these curves. These tend to be the ones that drop down a lot more at the beginning and then kind of move more steep here. If we look at the ones near the top, okay, these are the ones that tend to start a little bit higher and then stay lower for a little bit longer. And kind of a nice thing about this approach is it also allows you to see the outliers, right? So here's one hypothetical outcome that didn't really fall in the bulk of the rest of them. You see it's quite a bit lower out here. This looks like another outlier. Yeah, so it doesn't really have as much of a dip at the beginning. And this is just using the same kind of strategies that we discussed in the time series and kind of original D3 lectures. It's just a dynamically linked scatter plot and line plot. Okay, so kind of a really nice idea. Kind of sometimes when you just take pure statistics class, we'll often be talking about uncertainty in parameters. So you will see the uncertainty in the linear regression coefficient or uncertainty in the mean. But what hypothetical outcome plots force you to do is think about how uncertainty in the parameters translates into uncertainty in the data, right? So, we're not simply showing like a histogram of the slope coefficient, even though you could show a bootstrap histogram of the slope coefficient, but that tends to be something only statisticians will understand. It's better and it's more widely accessible to show uncertainty in the data space, not the parameter space. So it's forcing us to think about how the uncertainty in the parameters translates to uncertainty in the original data, or what the model viewed in the original data. Okay. And then the last point, even though we are kind of focusing mostly on just curves in this lecture, the same kind of idea applies in a lot more settings. So I've linked some examples where they have hypothetical outcomes in network data and in geospatial data. But the same kind of principle applies. Is imagine what alternative outcomes could have been for your data and for your model and visualize them in the data space.